Swayam Prabha. Digital India. Educated India.
This maritime engineering, as you see, is a very special program which has got multidisciplinary input from mechanical, civil, structural, aerospace, naval architecture, chemical engineering, electrical, electronics, applied mechanics. It's a multidisciplinary program. You will find this program is completely different, dedicated to industrial training and thorough capacity building on the new trade of maritime sector. It's a grooming economy which will give you a lot of job opportunities and research frontiers as far as India is growing. And the Blue Corridor effect, which is planned by Government of India, is one of the important mission which requires maritime engineering growth to happen in the country. So this program caters to expected that capacity building in this program.
Friends, this is part of a material science engineering laboratory which becomes one of the teaching aid for the maritime engineering program. So when you talk about materials innovation in maritime industry, though concrete and steel have been conventional candidates of choice for engineers, for example, we have titanium vessels, high-speed craft boats made of fiberglass. These are all advanced materials which actually do not come across conventional standard design code of practices. We conduct box furnace test, tube furnace test, vacuum arc melting, induction melting, vacuum induction melting, vacuum sealing unit, which are all present in this laboratory is a small segment of material science laboratory. Friends, a typical furnace where the operating temperature for testing specimen can go as high as 12 degrees Celsius. Generally at room temperatures and ambient condition, the mechanical properties will not alter much. As you see in the course lectures, you will notice that strength of the material get degraded when the temperature rises beyond 600. Therefore, when you talk about fire resistant design, you must also choose an alloying element such a manner that the strength doesn't degrade beyond 600 degrees Celsius at all. Welcome to the ambience of IIT Gandhinagar Lecture Theatre. This is one of the interesting classrooms where the maritime engineering classes will be conducted. We have got state-of-the-art projection facility and good audio-visual recording systems. Once the lecture is over, you see the system here. We can generate the PDF files of the lecture directly and you can email the PDF files directly to your email IDs. So it's a state-of-the-art facility we have in IIT Gandhinagar where the lectures are lifetime recorded and shared with the students immediately. This is the IIT Gandhinagar library. This has got all collections of books which are referred as the standard textbooks and references for the course and the program. It also has lot of online editions of design code of practices and reference materials and e-collections of various video lectures of international courses and programs related to maritime engineering. We will be taking you around to the advanced material manufacturing units. So you will have state-of-the-art facilities available at IIT Gandhinagar. So welcome to the program to join MTech and PhD at IIT Gandhinagar Maritime Engineering. So please try to enjoy and take the advantage of this to the maximum. Welcome to the program and welcome to IIT Gandhinagar. Friends, welcome to the lecture 34 of the SwayamPrabha course on maritime structures offered by Department of Maritime Engineering at IIT Gandhinagar. This is a sequel lecture of the previous one where we are going to discuss about the design procedure for tubular members. In the last lecture, we discussed about the procedure for members under axial tension. So, under axial tension, we need to work out the allowable tensile stress. Which is given as Ft, allowable tensile stress in tension, which is 60% of the yield strength. When you talk about members under axial compression, it is not that straightforward like tension because axial compression can cause buckling. So one has to check whether the member is under pre-buckling load or not. So there are two parameters which will control this. The one first parameter is the d by t ratio, the diameter by thickness ratio. So, if it is less than 60, you have a different procedure. If it is more than 60, you have a different procedure. So, first cutoff happens at d by t value. The second cutoff happens at KL by R value. You know, L by R slenderness ratio, which we know for factors useful in calculating the buckling loads, Euler's buckling load, Rankine's load, etc. So, similarly here K is identified as effective length factor which we discussed in the last lecture, a few numbers as given on section 3.3.1d of API RP2A, and of course L is the unbraced length and R is the radius of gyration, which is actually square root of I by A, where I is the moment of inertia of any governing section and A is the area of cross section. So, one can find out this, and between the value of d by t and KL by R parameters governing, one can find out the allowable axial compressive stress. If KL by R less than Cc, where Cc is given as the critical compressive stress, which is 2 pi square E by Fy, the wholes to the power half, that is Cc is given as square root of 2 pi square E by Fy. If KL by R is less than Cc, then in the last lecture we gave you the governing equation to compute the axial compressive stress. If KL by R is greater than Cc, then Fa is given by 12 pi square E by 23 KL by R the whole square. Friends, this is true when d by t is less than 60. If d by t is more than 60, then in the equation Fy will be substituted as Fxc or Fxe, whichever is less. Let us see what are these two values. Now, when d by t is exceeding 60, the member is expected to undergo or expected to experience local buckling. Therefore, one should be interested to compute two quantities. One, the elastic local buckling stress, which is given as Fxe. The other one is inelastic local buckling stress, which is given as Fxc. So, amongst these two, whichever is a lesser value, that will be taken as a substituting value for Fy in the previous equation. Here as well as the equation which will compute Fa. So, let us write down the equation for Fa. We know the allowable axial compressive stress Fa is given as 1 minus KL by R square by 2 Cc square divided by 5 by 3 plus 3 KL by R 8 Cc minus KL by R Q by 8 Cc cube times of Fy. Now, this Fy will be changed to be the least of Fxc or Fxc, that is elastic buckling stress or inelastic local buckling stress. Let us see those equations now. Furthermore, also friends, in Cc, what you see here, you also have 2 pi square E by Fy. So, you also have Fy here. Even this Fy will also be substituted the least of Xc and Xc. Now, let us see what are these values. Fxc, elastic local buckling stress, is given as 2 C E T by D, where C is called the buckling coefficient. Usually this value is taken as 0.6, but looking into the imperfections, construction difficulties and the material degradation of standards in quality control, etc., code advises C to be taken as 0.3. So, C is known to us. Of course, E is modulus of elasticity, which we know for steel. T and D follow usual conventions. So, I can compute Fxc straight away from this equation. Now, let us see about the inelastic buckling stress Fxc, which is given as 1.64 minus 0.23 d by t to the power 1 by 4 times of Fy. This is true if it is less than or equal to Fxc. If not, Fxc can be straight away taken as Fy. So, friends, now we compute Fxc, least of this will now become Fy, and I use that Fy in this equation to compute the allowable axial compressive stress when d by t exceeds 60. Okay. Of course, this is true when d by t is less than or equal to 60. Okay. Then let us move on to the next aspect of the stresses, which is bending. The allowable bending stress Fb is given by the following equation. So, Fb is given as 0.75 Fy if d by t is less than or equal to 10340 by Fy. Otherwise, FB is given by 0.84 minus 1.74 FYD by ET times of Fy if 10340 by Fy is lying, d by t lies between this value and double of this 2680 by Fy. I mean double of this. Okay. So, FB can be now computed with this. Furthermore, minus 0.58 Fy d by t times of Fy if d by t lies between 2680 by Fy and 300. Friends, it is very interesting. If d by t exceeds 300, then it is not recommended, because the pre-buckling load will be quite large. We can see an example. Let us say I have a member of 1000 mm diameter, I am using a member of 20, okay, or let us say a very thin member 10 mm, or I will use member of 1500 or 2 meter diameter external and thickness is maybe 5 mm, let us say. Okay. So, this value now becomes 400, which exceeds 300. So, the member will undergo serious local buckling. So, it will not be able to sustain the bending load, therefore, they are not recommended for offshore applications straight away. Okay. So, now FB can be computed with these three equations depending upon the ratio what we have for d by t. Okay. So, the allowable bending stress FB can be computed straight away using this. Let us move on further to find out shear. The maximum shear stress which is given as FV is given by 2 times of V by A, where FV is the maximum shear stress used for the design and A is the area of cross section, V is the transverse shear force. Now, the allowable is the maximum shear. The allowable shear stress FV is given as 0.4 Fy. So, we have the allowable value, we have the maximum value. Okay. So, this can be helpful to compute the shear stress on the members across for the design. The next one should be the torsional shear. The maximum torsional shear stress FVT, the maximum torsional shear stress, is given as MT d by 2 by IP, where MT is the torsional moment in meganewton meter. IP is the polar moment of inertia in meter 4. Of course, D is the diameter of the member. Outer diameter of the member in meters. So, the maximum torsional shear stress given by this equation and the allowable torsional shear stress is given by which is FVT is again similar to the permissible shear, which is 0.4 Fi. So, friends, we have the governing equations for finding out torsional shear, bending shear or the beam shear, bending, compression and axial tension. We will now move forward to hoop buckling stress. The elastic hoop buckling stress and the critical hoop buckling stress will govern the design. Let us see what are these values. The elastic hoop buckling stress which is given as FHE is actually given by the equation 2 CH E by TD. Related to CHE T by D. Now, CH is the elastic hoop buckling stress coefficient, which is given by .44 T by D if the torsional moment applied is more than or equal to 1.6 D by T. Where M here is given as a geometric parameter. It is not a torsional moment, the geometric parameter which is given as L by D square root of 2D by T. So, we have already discussed that in most of the time in maritime structures, we always deal with form dominant design. You will see in most of the cases, the allowable stresses are governed by D by T ratio, L by R ratio, some geometric parameter M. So, these are all an example illustrated to strengthen the discussion that for maritime structures, we prefer to use form dominant design. So, M is a geometric parameter, you work out M, where L in this case is length of the cylinder or length of the tubular member between the stiffening rings. Okay. Now, CH is equal to 0.44 T by D plus 0.21 D by T Q by m to the power 4. This is true for condition 0.825 D by T m less than 1.6 D by T. Let me take out this and write down here where L is length of the member between the stiffeners. Then further, CH is equal to 0.736 divided by m minus 0.636 if m is between 3.5 and 0.825 d by t. CH is given as 0.755 by m minus 0.559 for m lying between 1.5 and 3.5. CH is taken as 0.8 if m lies less than 1.5. So, you know the elastic or the critical hoop buckling coefficient CH depends on the geometric parameter m, which is actually used in this equation to compute the critical hoop buckling stress, which is actually based on linear stress strain relationship. Now, let us move on to find out critical hoop buckling stress. The material yield strength related to this elastic hoop buckling stress determines whether elastic or inelastic hoop buckling stress will occur. So, let us say the elastic buckling if it occurs, then the critical hoop buckling stress will be as same as the elastic hoop buckling stress given before. So, FHE is already we have here, So, the critical hoop buckling stress will be same as this if elastic buckling occurs, and this is true for a condition that the elastic buckling stress is less than 0.55 F5. So, there is an upper limit of this. In case the material undergoes inelastic buckling, then the critical stress is given by 0.45 Fy plus 0.18 FHE. This is true for FHE lying between 0.55 Fy to 1.6 Fy. FHC is then given by 1.31 Fy by 1.15 plus Fy by FHE ratio if FHE is lying between 1.6 Fy and 6.2 Fy. For the FHC is same as Fy if FHE exceeds 6.2 Fy. This is about the hoop buckling stress critical value. The next one what we are interested is the ring design. Ring design actually is the governing member for improving the circumferential stiffness. What in layman's language we call as ring stiffeners. Now the ring stiffeners has got two parameters. One is the cross sectional dimension leading to moment of inertia about the bending plane. Second is the spacing. All along the member, at what spacing you would like to have the stiffeners, and if at all you have a stiffener, what will be the cross sectional dimension of the stiffener. So, two parameters. Let us now see one by one. The moment of inertia required. So, IC is the moment of inertia, the stiffener. Let us say meter to the power 4. Required will be governed by T L d square by 8E of FHE. Now, L in this case is the spacing of the stiffener. So, what actually you do is, you take a cylindrical member, decide the cross sectional dimensions of it. Can be an I section, it can be a channel, and so on. So, find out the moment of inertia of this section, substitute here, whereas D in this case is the diameter of the external ring. Okay. So, if you have got a composite section, you should find out the diameter at the centroid of the section. So, you compute IC, D is known, E is known, thickness is known. Okay. So, one can compute the spacing. On the other hand, you fix the spacing maybe at 3 meter, 4 meter intervals, compute the required IC and provide the section. Either way you can do the design. Okay. So, friends, we have understood that the members essentially tubular are subjected to axial tensile stress, axial compression, which can lead to buckling mode failure. Therefore, the parameters govern will be d by t, then k L by R and Cc. Then bending stress, shear stress, torsional shear, hoop buckling stress, then the ring design. So, now it is very easy for us to find out the member cross sections or to check the capacity and demand for a given system of offshore platform or jacket structures or any tubular member comprising the system under different conditions of loading and behavior like tension, compression, bending, etc. So, this appears to be very straightforward and simple because equations are very clear and the limitations are given and equations emphasize form dominant design. So, they look very similar and very straightforward. But friends, it is not that easy. The difficulty comes when they are under combination of loads. So, what do we understand by combination of loads? How can they combine? For example, axial compression and bending can get combined. Then there is a possibility of axial tension and bending get combined. Then the third combination could be axial tension and hydrostatic pressure. The fourth combination could be axial compression and hydrostatic pressure. Hydrostatic pressure can act under two conditions. One, it can act on stiffened cylinders. It can also act on unstiffened cylinders. Stiffened cylinders are those members which are provided with circular stiffeners, ring stiffeners along its length as we discussed in the previous slide. Unstiffened are those where there are no such ring stiffeners. So, when the tubular members are under hydrostatic pressure, then the membrane stress which is Fh is given by Fhc by Sfh. FSC we already calculated as elastic hoop buckling stress critical. See here, we already computed that. I will show you. We already computed that for different conditions. This is for inelastic buckling, which is called critical hoop buckling stress. For elastic buckling, this is different. For inelastic buckling, this is different. Depends on the conditions as we see here. Okay, so FHE, HC is known to us. Okay. SFH is a safety factor. Against hydrostatic collapse. Let us see what are the typical values we have for this safety factor. The typical values of the safety factor against hydrostatic collapse as per section 3.3.5 of API RP2A, depending upon the design condition, under different combinations of loading like axial tension, bending, axial compression and hoop compression. If I use basic allowable stress, is used in the design, then this factor is 1.67. This is depending upon the ratio of Fy by Fb, and this can be taken between 1.67 to 2.0, and this can be taken as 2.0. If in case only 1/3 increase in allowable stress is used, is permitted, then this number goes to 1.25 and this number goes as Fy by 1.33 Fb. This varies from 1.25 to 1.5 and this goes as 1.5. So friends, in this equation, safety factor against hydrostatic collapse is known to us. FHCC is the critical inelastic buckling stress known to us. So you have to limit the membrane stress thickness to be safe against hydrostatic pressure within this. Okay. So we have seen that various combinations of loads also govern. Therefore, it is not simple that you compute straight away these forces and then you compute the stresses, find allowable value and the actual value and check for the design as capacity and the demand comparison. The problem comes when they are combined. So in the next lecture, friends, we will discuss about the combined effect of this and we do an example problem and see how the combined effect can be illustrated with certain set of equations as we go ahead. So friends, in this lecture, let us summarize what we have learned. In this lecture, we learnt about axial compression, permissible stresses. We learned permissible stress under bending, shear, hoop stress, hydrostatic pressure and the ring stiffener design. So, we understood that what are the possible load combinations that can happen and how they can become critical. In a nutshell, we also understood that most of these equations are form dominant. They depends upon the cross section, essentially d by t, then KL by R and so on. So, they are form dominant and mostly they are applicable to tubular members. So, our focus was totally on tubular members because tubular members are most commonly used in offshore construction for oil and gas exploration platforms. Hope you have followed the lecture. I would always urge you to have an original copy of API, RP 2A from the Institute Library or from the Society, American Petroleum Institute. So, to also follow the upgrades of these equations time to time and try to understand how these equations get modified with the commentary given by these codes for us to understand. Thank you very much. Namaste.